Okay, so in this tutorial, we're going to cover the basics behind the Web Audio API in the interest of creating an algorithmically composed piece of sound or music for our assignment. And just covering the basics is actually going to give us enough to do some interesting algorithmically composed music or sound. Well, mostly covering the basics. I think we're going to need to cover all of the basics. Probably it'll be nice to talk a little bit about audio buffers, and we're going to need to talk a little bit about music theory if we want to make algorithmically composed music and not just algorithmically composed sound. But we're going to stick to the basics. So I'm going to make a video where I'm just going to go through all of the basics, and then I'll follow that up with a video for the assignment, how we can use those basics to create a composition. Now, I've got plenty of deep dive material here. I've organized, like I mentioned, a whole bunch of notes for you to go into. I can make subsequent videos where I get into some of this other stuff, or you can kind of peruse these notes on your own. Granted, it's probably arguably easier to kind of make sense of these notes with some accompanying videos, but I'll let you all let me know if that's of interest, or if after doing these videos, we're ready to move on to another API like the 3D stuff. So, we'll play that by ear. But one thing that why don't we just jump right in, and then I'll come back and talk about some of this other stuff. And actually, I'll keep this page open so I can come back to that home page later. If we want to use the Web Audio API, we need to create a web audio context. So this is always step one. If you messed with the Canvas API directly, right, instead of using the P5JS library, if anybody went into some of those deep dive stuff and just used the Canvas API, this might look familiar, because in order to use the Canvas API, we first need to create a Canvas context. Same thing with the 3D stuff. This is kind of a convention with these web APIs. We create a variable that's kind of our main context from which we can then start to do all this other stuff. So this is how we create an audio context. So I'm going to, as I follow along these notes, I'm going to be kind of setting up the project that eventually will become our assignment. I'll call this Algo Muzak. Muzak, by the way, is this old defunct, I don't think it exists anymore, company that used to make like background music for like department stores and like elevator music. Right, so like a department store might have, I think these knobs actually existed. I'm not totally sure. At a department store where you could turn the background music of a, like a shoe store higher or lower. I find this company, just the whole idea of a background music knob, fascinating. And in the spirit of that, I'm going to call this algorithmically generated Muzak, Algo Muzak. And actually, the kind of music that we're going to make is going to be kind of chiptune-y. Maybe I should name the repo that, but I'll come back to that in a second. Let's just create an index, or actually, let's go ahead and I'm going to open this up in Atom. And I'm going to create an index page, right? Because all web projects need, at the very least, one HTML page. I'll use Atom's shortcut here to create that template. I'll call this Algo Muzak. And then I'll also create a JavaScript file. I'll just call it main.js, where I'm going to be writing all of my web audio code. And I'll have to, before I forget, make sure to, misspelled script. Make sure to import or link that script tag, that JavaScript file, into my HTML page. And let's open that up. And open my, don't want to take a screenshot. I want to open my developer tools, my console specifically, so that I can catch any errors. And we should be ready to go. Now I want to talk about this long line of code just for a second here. In theory, we could do this. And actually, in theory, we can do this because the window object is implied. Window is sort of the global object that all the variables we create are kind of inside of. So sometimes you see people write things like window inner width in their code, but sometimes you'll just see developers write inner width. You don't. The window is sort of optional. But this is a bit more verbose. But in any case, even if I had done this, why this longer one than this longer one? Well, because in some browsers, audio context works, but in some browsers, audio context doesn't exist. And it's called WebKit audio context, specifically Chrome and Chromium, Safari, which all use this underlining browser called WebKit. So in order to be safe, what we're doing here is we're saying we want to create a new audio context or, right, this means or, a new web audio context. And what's going to happen is if this doesn't exist, then it'll default to this. But if it does exist, it's going to use that. So this is just a way of creating an audio context that ensures it's going to work regardless of the browser that we're using. So that's the reason for this long, annoying line of code. But once we've got that audio context created, we can use it to do all kinds of web audio stuff. Like creating sounds. So that was an oscillator node. Hopefully you can hear that. My mic, I have my audio set pretty loud on my speakers, which is going to drive me nuts and my neighbors probably nuts. But it's hard for the microphone I'm using to pick up other sounds beyond the one that's right in front of it, like my mouth, because it's a directional mic. So hopefully that's coming in audibly. But if not, you can also check out these, obviously, or you should be looking at these examples on your own. But also take note that it's going to play automatically. So if you have your sound high, this is going to startle you. Because all the code you see here is actually running on these example pages. I did that on purpose so you can do things like open the dev tools here and actually manipulate, like actually play with the, that audio context and do stuff in here. In case you wanted to debug or experiment with some of this stuff. So the first thing we do is create a source node. So there's 3 types of what we call nodes in this audio context, in this web audio API. We have a source node, so that these are the nodes where sound originate from. Then we've got processor nodes, which are the nodes that can, like the name implies, process sound, so change it, manipulate it some way. And then we've got one analyzer node, which, like the name implies, analyzes the audio. And you might, why would you analyze the audio? Well, for different reasons. One example I'll show real briefly in this tutorial is you want to use it to visualize our sound, our audio. So analyze the data in our audio and use it to create an image from it and understand what's going on in our audio that way. But you can also use it to analyze sound to do things like do beat detection, figure out the rhythm in a song, or do pitch detection, do some analysis on pitch and things like that. So this is for analyzing the sound. So this is kind of a little bit of an oddball, but mostly when we're creating algorithmic compositions, we're going to use source nodes and processor nodes. Now, I'm just going to be using one type of source node, which is the oscillator node. In these tutorials, again, unless you want me to do some other deeper dives and tackle some of the stuff I get into in some of these other deep dive notes that I put together. But I'll just say that beyond the oscillator node that we're going to use, there's also a WebRTC stream. We can use that as a source node. So WebRTC is another API, which we've talked about. WebRTC is how we do like do video chatting and stuff like that. It's how we pull like real-time video and audio from our devices, but it's also much more interesting than that, right? Because it does peer-to-peer connections and other stuff. But we can use the WebRTC API to pull the audio from a live stream of some kind, our microphone or our cameras, our webcams, and send that into our web audio context and use that as a source. Or we can also use the audio tag and the video tag, right? So if you in your HTML page, you load up a sound or a video, we're using the audio or video tag, that could also be a source for the web audio context. Or, and I'll talk about this one a little bit because it's part of the web audio API, there's also the audio buffer source node, which is how we create sound from scratch. I love this one. We're talking like creating sounds from raw data. So this can be used for doing things like creating noise, which I will talk about a little bit in these tutorials, but we can also create our own sine waves and oscillators from scratch, or we can use it to load sounds from files, like from MP3 files or WAV files, so we can use it to do like sound sampling. And we could also use it to load up what are called sound fonts, which are used a lot in like MIDI tools and MIDI, drum machines and stuff like that. So we can create all kinds of sounds out of pure audio buffers. This is a surprisingly low level access to an otherwise pretty high level API, which I love about this web audio API. But I'm not going to get into that here. For simplicity's sake, we're just going to be using the oscillator node, which is a quick and easy way to create simple tones like sine waves and square waves. So the music that we're going to create is going to be a little bit like chiptune. I don't know if folks are familiar with chiptune, but this is a genre of music, of electronic music, where musicians use like old game consoles or things like Game Boys and Commodore 64s and stuff to create music. The idea here is you're using the chip inside of those machines so that you can kind of get these lo-fi, sort of old school 8-bit sort of sounds. And these are folks, you usually, the instrument of choice is a Game Boy. People actually like mod out their Game Boys and create super rad Game Boys and then like actually literally perform with those Game Boys, like perform live, like at shows with like tons of people that come out. It's a whole scene. Look at this guy crowd surfing, playing his Game Boy at a chiptune show, at a chiptune festival apparently. World's biggest chiptune festival. What is that? Oh, Blip. Oh yeah, this is actually a really popular Blip festival. This one's in Tokyo, but it's also they've held it in New York and stuff. So chiptune, it's a whole scene. It's very cool. And the way the musicians make this music actually is like there's actual Game Boy cartridges, like this one, LSDJ, which is essentially a program to make music for Game Boy. You put it into your Game Boy, and then you get a program that looks like this. It's a better screenshot. I don't know. It's a better screenshot, where you can then pick the notes that you want to play. Now, the music we're going to make, I'm making this comparison to chiptune, and if you haven't listened to chiptune music, totally recommend it. You should look up some chiptune musicians. But the reason I'm comparing what we're doing to chiptune is because it's going to be similar in a few ways, but different in others. It's going to be similar to chiptune in that the sounds, the timbres, the textures, the types of noises we're going to be making to construct music is going to be these lo-fi oscillators, these really simple digital computer type sounds. So it's going to sound like chip music in that sense. And it's also going to be automated, right? So we're going to write code that just runs in our browser and plays the music, right? We're not necessarily going to be playing the music like an instrument, though I might show that a little bit, because again, we can do anything with this web audio API. We can construct instruments with it if we want, but in our particular case, we're going to be creating algorithmically composed sound and music to kind of stick with this theme that we've kind of introduced so far this quarter, right? We created algorithmically composed ASCII art in the terminal. Then we did algorithmically composed images using the Canvas API and in particular the P5 library. And so now we're going to revisit that same practice, but in a new sort of API and media here. We're going to use sound and music to create algorithmically composed music. But the Web Audio API can also be used to do all sorts of stuff essentially anything related to sound and music. But in doing this, our compositions will be automated, which is to say we're going to write code that then just plays the music automatically. We're not going to be performing it like an instrument. And chiptune is that way too. A lot of these musicians perform, like they'll switch between different, pre-written bits and pieces, but it's ultimately automated. This is like a piano roll. I don't know if folks are familiar with piano rolls, but there are these like player. I should search instead. Player piano. Player pianos are these automated pianos that have these piano rolls in them, which are these little punch cards, which then automatically perform whatever composition has been encoded into this piano roll, this punch sort of tape here. So this piano can actually like play itself. And this is like chiptune in that way, except that this is piano sounds and chiptune is Game Boy sounds. But they're both similar in that you pre-write all the notes in the order and the time, and then the Game Boy just plays it. Or in this case, the piano just plays it. So it's automated. So our compositions will be automated, like the player piano and like chiptune. Our compositions will also include lo-fi sounds because we're only going to be using the oscillator node. We're not going to be experimenting with any other sources because that's a little too much for this intro video. So it's going to sound like chiptune. It won't sound like a piano. But unlike the player piano and the chiptune, ours is going to be algorithmically composed, right? These compositions are written by people and then encoded either using LSDJ or punched on tape. But we're going to create rules, algorithms, which then generate the compositions themselves, just like we did with our visual compositions and our ASCII art compositions, because we're creating algorithmically composed sound or music. Okay, so let's continue going through this API to sort of get to the point where we can make some algorithmically composed music, beginning with our first type of node, a soc node, and we're going to be just sticking to one kind, which is the oscillator node. So to create an oscillator, we do this, and actually I'm going to call this tone. So the audio context object has a whole bunch of methods inside, what are called factory methods, which can be used to generate these new instances of these nodes. And this is the one we use to create a new oscillator node, and it'll store in this variable an instance of that node. If I save this and I refresh my page, our dev tools here, the maybe main purpose of this console, as we've discussed before, is to catch any errors, right? Like if I misspell this and I refresh, I'll get an error that says create oscillator doesn't exist. This isn't the function. That kind of clues me into the fact that I misspelled it. If I save, refresh, now I have no errors. But this console here is giving me direct access to the JavaScript that I've written on my page. So as soon as I type in tone, I can actually see that object, and I could actually hit enter, and then I could inspect it. And I can see that this oscillator node that was created by the create oscillator has all kinds of properties and methods, or rather built-in variables or functions inside of this object. So what that means is we've got tone dot, all kinds of things. Maybe most importantly, we've got a tone dot type, and we've got a tone dot frequency. Our type by default is set to sine. So we have a sine wave by default, and our frequency has a value set to 440 by default. So when we say type sine wave, what we're essentially defining is the texture of the actual sound. In music, we might use the term timbre, so timbre or texture of the sound. And when we say frequency, what we're talking about is the pitch. So in physics or math, we would use this term frequency. What is the hertz, the measurement of oscillations over time of that sound, because that's what sound is. I mean, it's oscillations in the air. And so we can measure those oscillations in terms of its frequency. But in music, we would call frequency pitch, right? We use different lingo in music than we do in mathematics. And so 440 hertz is the frequency. And this particular frequency in musical terms, we call A, or specifically A4, the fourth A key in the keyboard, in the piano, which is essentially the one in the middle, the A key directly in the middle of the piano. So this is the pitch, 440 hertz or A4. This is the default value if you don't specify another value, and this is the default value for the type if you don't specify another type. But we have other types, and obviously we can set any pitch. Humans can only hear between 20 hertz and 20. I think this is right. I'm going off memory here, but you can Wikipedia fact check me on this. Or maybe we're talking, I think it's 20 hertz to 20k hertz. I think that's right. So if you put anything lower than 20 hertz, you're probably not going to be able to hear it. Your computer is going to generate the sound, and it'll be coming out of your speakers. Your speakers will be vibrating, and thus at that frequency, and thus moving the air particles in space and generating the sound. You just won't hear it. Maybe your dog will, but you won't. And if you go beyond any number higher than 20k, you also won't hear it. To be honest, this is just, not all human beings are identical, right? This is a general range. I think most people, probably cap out at like 17k. But if you want to test what your the highest frequency that you personally can hear is, you can just keep changing this value until you don't hear it anymore. But be warned, the closer you get to 17k, the like, right, the higher pitch, that more squealing and the more kind of like unnerving it's going to be. The lower the number, the lower the sound is going to sound. So this will change that frequency, right? Like what's the actual pitch? Okay. So that's our oscillators. Now, if I just make this and I refresh, I'm not going to hear anything, because I actually need to do a couple of things. I need to start this. I've created this oscillator, but I haven't actually started it. It's not generating the sound yet. It's just prepped. And I need to connect it to my speakers, or connect it to something ultimately, so that I can hear it. So first, that connection. These source nodes all have a connect method. Whether it's the oscillator or any of the other source nodes I mentioned, they all have this connect method, as do the processor nodes, which allows me to connect the output, the sound that will be coming out of this, to something else. At the very least, I need to connect it to CTX destination. The destination property of our audio context is going to be whatever your computer's default audio output is. So here's my audio settings. I have a few different possible outputs here. I've got my HDMI. This is my monitor, the monitor that I'm looking at right now. So that's my output, but I could have also changed it to my laptop speakers or my headphones, or I have a recorder that I've got plugged in, which is how I'm recording this screencast here. And I could change the output. And if I change my system preferences to another output, that's what CTX destination is going to be. So this is whatever your default system output is. So in my case, the speakers of my HDMI monitor, that's what I'm connecting my tone to. So now that I've got it connected, I'll be able to hear it. But again, if I refresh, I'm not going to hear anything. I actually need to start playing that sound. So again, I mentioned before, we've already got this tone object in here, so I can just run it here. I'll say start. And I'll say stop. And then it stops. And if I say start again, I get an error. So let's talk about this, and then I'll come back to start and stop. So the way the web audio API works is that once you've created a source node, and you've started that source node, and you've stopped that source node, the node gets trashed. It gets, like, the web audio API throws it away. And that might seem kind of annoying or frustrating initially, right? In a hyper simple example like this, where I might be like, oh, cool, I'm starting, I'm stopping, I want to start again. But it's actually pretty useful as we start creating more complicated projects, right? Beyond this, couple lines of code example here, you'll notice that, and you'll see this in the next video when we start creating the algorithmic compositions, is we'll be creating functions that'll generate different sounds. And a composition is going to be made up of more than just a single tone, right? I mean, in theory, you might have an ultra minimalist composition, but in theory, we're going to have lots of different notes being played, and the notes will start and they'll stop at different times. And if the web audio API didn't trash this source node after I stopped it for me, then that means in a more complicated program that I write, I would have to be responsible for trashing that getting rid of that object myself. Because if not, I'm going to leave it in memory. And if I create lots of sounds in a composition, I'm going to be wasting a lot of memory, and that could lead to problems like memory leaks or running out of RAM in my CPU and stuff like that. So it's actually kind of nice in classic JavaScript fashion. The API is going to just get rid of trashing that for us, so we don't have to worry about thinking about that. We can just create our sounds and let the computer trash the data when we're not using it anymore. But this can be a little, this can kind of blindside you if you're not aware that that's happening initially. Keep in mind, after you stop playing a source node, it's been trashed. And if you want to create another sound, you got to create a new source node. But we're going to make that easy on ourselves by encapsulating some logic and functions when we get to the assignment. But we'll come back to that. So start and stop. Obviously if I refresh, I get a fresh new tone object. So if I refresh the page, I can start it again and stop it again. But if I try again, it's trashed until the next refresh. Now, something to keep in mind here about start and stop is that if I did this, right, and I refreshed, I don't hear anything because all my code runs as soon as the page loads, which means I said start, stop immediately. I mean, we're talking fractions of milliseconds after each other here. So not enough sound is generated to actually create a sound wave. We don't actually hear anything. These functions aren't so much triggers as they are schedulers. We're scheduling the start of a tone and we're scheduling the stop of a tone. Scheduling it according to what timeline? According to the audio context's timeline. So this CTX object has a property called current time, which keeps track of the time since the creation of that variable of the audio context. Whoops. So like every time we take a look at this current time, we see how many seconds have passed since the page loaded, essentially, right? Because this variable is getting created as soon as the page loads. If I refresh, it's been 2 seconds, 3 seconds, 4 seconds, 5 seconds, and so on and so forth. And it keeps counting. There's an internal clock. And this clock, by the way, that the web audio context is using to keep track of how much time has passed since its creation runs on a separate thread from the rest of our JavaScript code in the browser. So for non-computer science folks in the class, what this means is typically, and I'm going to drastically oversimplify here because this is not a computer science class, this is an art class, but just so you know what this means, in a CPU, on a computer, we can run code on separate threads. And threads are like different lanes on a highway. And our program in this metaphor is made up of a lot of cars, right? We got a lot of pieces and modules and functions. These are all different automobiles running on this highway, running through our CPU. And our CPU has multiple lanes on it, multiple threads, so that it can be doing processing more than one thing at a time. If we write a program and all the code in our program runs on the same thread, it's kind of like if all the cars on the road are on the same lane, which means you could imagine if one car in front is slowing down, it's going to delay all the cars behind it, right? It's going to create a sort of a traffic jam. Which is why, like, if you're in a web, and most JavaScript code runs on a single thread, which is why if you're creating a really complicated NetArt piece, maybe it's got a lot of interactive 3D graphics and stuff, and there's some part of it that starts slowing down, the whole program's going to slow down, right? It's going to feel like the whole thing is freezing. The audio, though, is not going to be affected. It's going to run on a separate lane, and that's important because, if there's a little bit of a lag in a visual piece, right? If a frame gets dropped in a canvas animation, it's not really the end of the world. I mean, depending on how picky you are as an artist, but it's a lot more noticeable with sound. Because if you have a musical composition, right, let's say you're performing, and maybe you've created a tool to do live audio at a show using this web audio API, and you're creating real kind of like clubby, housey, trance sort of type of music with a real kind of consistent beat, like boom, 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 boom. If some other part of your application, like the visuals you created to maybe because your app also does real-time visuals, or maybe because you have an interface to interact with the code that you wrote or whatever it is, if that introduces a little bit of lag, your boom, boom, boom will stutter. It'll be boom, 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 boom. And now that's a whole different beat, right? So now we're talking about that mistake in the code is quite literally changing, the dance on the dance floor or whatever, right? So for all these reasons, this is going to run on a separate thread. So the code won't conflict with each other. But what that also means is, and what you've maybe noticed, is that this clock counts in seconds. The typical JavaScript clock, right? The one we use when we create a date object or when we use the set timeout or set interval, you've noticed we set time in milliseconds, right? So we would write 1,000 if we wanted to wait a second. But here in the web audio clock, for whatever reason, the default unit of measure is seconds. So just keep that in mind. Seconds when dealing with web audio, milliseconds when doing any other JavaScript timing stuff. So coming back to start and stop, these are schedulers, not triggers. So this is scheduling a sound and scheduling the stopping of that sound. So at what time is it scheduling it at? By default, the default value, if you don't pass in an argument here, is going to be ctx.current time, meaning whatever time, current time, meaning whatever time it is right now, that's the time it's going to schedule this, which is why we didn't hear anything initially, because it played it and stopped it both at the current time. So it stopped it as soon as it started it. But if we say like current time plus 1, for example, if current time initially is 0, then this is 0, this is 1, our sound will play for a second before it stops. Right? So they're played for a second. Again, I hope you can hear that. If not, imagine a sound and, try this out on your own and you'll hear it. So that's scheduling. And, likewise, we don't have to start the sound immediately. We can say start the sound 3 seconds after the page loads and then stop it 4 seconds after, or I shouldn't say page loads, 3 seconds after the context has been initiated and 4 seconds after it's been initiated, stop it. So now if I refresh, 1, 2, 3, 4, right? So it started at 3 and stopped at 4. So that's what I mean when I say these functions aren't triggering the start and stop necessarily. They're scheduling it, and then later at the time specified is when we'll hear that start or that stop. So this is a source node, and how the source nodes just work in general. Oh, although I did want to show you this. Let's get rid of the stop and start. Let's hear what those different types sound like. So if I refresh and say tone start, and then I say tone dot, so that's a sine wave, but I can change it to a square wave, or a triangle wave, or a sawtooth wave. So those are the sort of the different types. Again, so this is what I mean by texture or timbre of the sound, right? It's the same tone, the same pitch, same frequency, but the texture changes. There's also, you can make custom shapes, which is something that I get into in these custom oscillator wavetable examples. But for now, to make our kind of chiptune music, those will definitely be enough types to play with. So there's a couple of different ways to create these nodes. There's actually 2 versions of this API, 2 different sorts of syntaxes that we can use. This is called the factory method. But we've also got something called the constructor method. Oh God, my spelling. Oscillator node, which looks like this. In the, let me write that, constructor method. In the factory method, the CTX object operates like a little factory that's got all these methods built into it that can then return these tone objects. This is called the constructor method. This is more the way, this is what object-oriented code looks like in JavaScript, where we have these classes. And we talked about this a little bit last week. I still kind of want to make that paradigms video that some folks asked for at our last video chat. But object-oriented programming is just one of these paradigms, one style of programming, where we have these classes, which are almost like little cookie cutters, little templates from which we generate new instances. We make new cookies, we make new objects modeled after the object defined in this class. And the method, the function inside of these classes that is used to generate that initial object, the instance of that object, is called the constructor. And when you create a class, you define a constructor. That's part of object-oriented programming when you're making your own classes. And the way that you instantiate, i.e. make new cookies from that cookie cutter, instantiate a new instance of a class, is using this new keyword in JavaScript. So this is the way that it looks, that most object-oriented programming looks like, which is actually why I kind of prefer this syntax over this syntax. I mean, that's, totally subjective, totally a preference, probably has a lot to do with the fact that I spend a lot of time doing object-oriented programming, so I'm, comfy with this syntax. But also, the other difference is that this version, the constructor version, I mean, obviously it takes some arguments. Specifically, it takes the audio context from which we are deriving this oscillator node, but it can also take a second object, a second argument, which is an object, which can be used to change the default values of its internal parameters, like this. Again, these are the defaults, obviously, but I could have made it a square wave and made it a lower pitch. That's not how you spell square. And I kind of just like the way this looks better than doing it like this. Let's make them exactly the same for comparison. Also, when you do it this way, it's not to say that you can't change it later. You can totally do this, right? I can instantiate this tone and then later change its type to square. So I still have access to those properties. This and this are creating the same object that I'm storing into this tone variable. What they return isn't different. It's just the syntax we use to create them that's different. So choosing between these is in part preference, and I prefer this one. But in part logistical. Like if I was constructing a more complicated application, I might have something where users are creating, maybe I'm making a musical tool in the browser and users are defining what they want their oscillators to be like. And then I can just take like whatever data the user gives me as an object and then pass that into this second argument, right? And so like this kind of helps me just design my software in a way that makes a bit more sense to me as things grow in complexity. But one reason why you might use this version instead of this version is that this version is actually it's better implemented across browsers. Specifically the shittier browsers, like Safari, probably Internet Explorer 2, don't have this version of the API, the constructor methods implemented. They only have the factory methods implemented. But this will work on all modern browsers, which is what we should be using in this class anyways, something like Firefox or Chrome or Chromium. We shouldn't be using Safari or Internet Explorer or any default browsers because they just generally suck, and let's not bother with them for this class. But if you're making something that, that you're going to release to a wide audience, like if you were making a musical tool for yourself for live performances, it doesn't matter, right? You get to choose what browser you're using. If you're making an installation for a gallery, it doesn't matter. You get to choose what browser is going to be in that installation, in that gallery. But if you're making a piece that people are going to be using online, they're going to be posting on a server specifically for any potential user to come and visit you, you might want to, when you're designing a project beyond Web Audio API, you want to think about browser compatibility, and you want to make sure you write your code in such a way that takes multiple different kinds of browsers into account. For example, this line of code, right, which I talked about before, takes into account the fact that we don't know the type of browser someone's going to be visiting the page with. So that being the case, this is going to be a bit more universal because the folks over at Apple did not bother to implement this version in Safari because Safari comes installed by default, so what do they care? No one's downloading Safari. They're not trying to sell it to us in the traditional sense. So screw them. Thanks a lot. But for the rest of this tutorial, I'm going to be using these constructor methods because I like them better. But feel free to use whichever you want. And just keep in mind, all the nodes that we create, the source nodes and the processor nodes, all have two different versions. Their factory versions and their constructor versions. So this is the constructor version. Okay, so let's get into processor nodes. So there's a lot of processor nodes. Like I said, processor nodes take some audio from another processor node or from a source node and manipulate it somehow. I've got a bunch of deep dive documentation into that here. I've got a section on all the core processor nodes, the gain node, which I'm going to talk about in a sec, the delay node, which is how we create delay effects, convolver node, which is how we create essentially like reverb, the kind of reverb effect, biquad filter node, which is how we do filtering, this kind of changes. I'll let you explore that. Wave shaper node is how we do distortion, so it distorts the sound. And with these core sorts of processors, we can create more complicated effects and processing. So things like fancier delays or ring modulators or choruses or flangers or all the other things you've seen guitar pedals for. We can create those by combining these different processor nodes in particular ways. So I've got a bunch of examples, deeper dives on that if folks want to get into other processing nodes. But for our assignment and for the sake of introduction, I'm just going to talk about one processor node, the gain node. The gain node, which again can be instantiated using both the factory method or the constructor method, right? So here is CTX create gain, similar to CTX create oscillator, but here is new gain node, similar to new oscillator node. And similarly, it has this options object, which I can use to set different defaults instead of doing it this way. What the gain node does is essentially change the volume. Gain is not necessarily it's not exactly the same as saying volume. Because we can stack gains together, and gain is more like we're even if we were creating this using analog electronics, we're driving the sound a bit, but for all intents and purposes, we can think of it as just volume. And this gain value goes from 0 to 1, 0 being volume knob all the way down, 1 being volume knob all the way up. So here we're cutting the sound in half. Now we're not really going to hear this unless we connect. Right now our tone is connected to our destination. But if instead we connect our tone to our gain, and actually let me call this level. If we connect our tone to our gain node, which we've called level, and then we connect our level to our CTX destination, then our audio is going to be going through the gain node before our speakers. So this is a little bit of a bummer. Little side note here. Firefox used to have amazing dev tools that no other browser had, including this web audio dev tool, which would actually look at your web audio code and create a visualization of the connections. So we'd say like, oh, you've got an oscillator connected to a gain, connected to a destination, and you can click on those and actually like modify the values and stuff. And so you could really debug your audio, web audio code and using the dev tools. They also had like a Canvas dev tool and a WebGL for 3D stuff dev tool, and it was glorious, and no other browser had it. And then Firefox did like this big major update like a year or two ago, which was generally good. It was great. The browser improved on a lot of practical fronts, but for whatever reason, when that happened, all these other dev tools also went away. And I've been meaning to ask somebody at Firefox why and to beg them to please bring it back. But in lieu of those visualizations, which I think are very helpful, I put some little sketch here together to kind of visualize what's going on in our code. So we created an oscillator node, we created a gain node, and we have our audio context. And we connected our gain node, our oscillator node to our gain, and our gain to our destination. So this is essentially a visualization of this chain, right? We're going from oscillator to gain to audio context. So the sound that's generated here is going to pass through the gain before it ends up here, and our gain is going to be cutting that volume in half. So now this is what it sounds like. Oh, wait 3 seconds. Let me change that to, and then we'll keep it at 1. Right, if I had made this 1, it's full volume. If I make this 0.1, it's a lot lower. You probably can't even hear that. So this will process the sound coming out of this oscillator specifically in this way, in that it's changing the volume. Last type of node is this AnalyserNode, which I mentioned before. Doesn't really change, doesn't affect our sound, nor is it creating sound. It's just whatever sound we connect to it, whatever sound we send to an AnalyserNode, it will give us tools for analyzing the sound, which again can be used to do fancy stuff like beat detection and pitch detection, which I've also got some other tutorials down here, deeper dives for other stuff we can do with analysis, but it's most commonly probably used for visualization, for seeing our audio. Also, something I want to mention about these visualizations, it's used for creating practical visualizations, kind of like useful visualizations. Something to keep in mind, because we're dealing with this web audio in this browser where we can also create visualizations in general using Canvas and WebGL, we can visualize our sound in all kinds of interesting creative ways. And if folks do want to do a deep dive video beyond the notes that I've put together on these audio buffers, that's something that I can also demo as a project, is how we can take sound. Actually, that probably should fit over here. In this visualization deep dive, if we do something there where we can take raw audio from a buffer and see it, right, and make decisions about how we want to translate, how we want to transcode our audio data into image data or into other types of data. But in this case, these are kind of like helpful visualizations, because it's not about getting creative or experimental with how we do that translation. It's about trying to understand some information about our audio. So in this case, what we're doing, what this one visualization is doing is taking our sound, and the height of these bars here correspond to the gain, correspond to the volume. So if we had full volume, then the peaks would be hitting the top of the canvas and the valleys would be hitting the bottom of the canvas. But since we're at half volume, they're only going, from the center a quarter of the way up and a quarter of the way down. And so we're only encompassing half the canvas with these lines because we're at half volume. So we can kind of visualize the volume here. The other thing that we're visualizing is the texture, the timbre of that actual sound. We've got a square wave, which means our oscillations jump. They do these sharp jumps when we go up and down. This is actually why we call this kind of sound a square wave, because when you visualize it, it looks like a square. And then we're also visualizing the frequency, the pitch. That we see based on the space between these oscillations. If this pitch was a higher frequency, these would be thinner blocks. The space between them would be less. If this was a lower frequency, like then these would be bigger squares. So we're getting a lot of information from this visualization. We can see the texture, the volume, and the frequency of the sound that we've generated. And this visualization was generated because we were able to analyze our audio using the AnalyserNode. This one, boom. And this is, again, the constructor method. We could have also used the factory method. Just like the other ones, create analyzer versus new AnalyserNode. And this visualization I made using just Canvas. So this is all the code used to create this visualization here. Actually, most of this is comments. I won't get into this again in detail in this video. I have notes for that over here, and also, I've got notes here that you can read. But if people are really interested, we can do a follow-up video where I get into that. But again, this is the native Canvas API, so I'm not using processing. And you notice it's not that much crazier, the code for the native API than with the library. But the real magic here is this FFT, or rather this AnalyserNode. This AnalyserNode is essentially an implementation of this algorithm called the fast Fourier transform. You can read about FFT on Wikipedia, but if you prefer a friendlier explanation, I've linked to this amazing article, this interactive sort of explanation for what the fast Fourier transform is, what exactly, and it also just helps you understand what sound is from a mathematical perspective. So this is a really rad interactive tutorial, highly recommended if you want to know exactly how the hell this is possible, what exactly the AnalyserNode is doing such that it can give us this information. But for now, we'll just take for granted that we can visualize the volume, the texture, and the frequency of any sound using this node by pulling the data that node gives us and using that data to create drawings in a canvas. Now, this just creates a still drawing, this particular code, but if we create an animation loop, we can visualize the audio in real time, right? So I've got flat because there's no sound now. And this is, so here's all the code that I'm using to generate this canvas. And we're doing that animation, that recursive function trick we did when we did our ASCII art animations, where we've created an animation function and we just call that function inside of itself on a set timeout, on a delay. In this case, I'm doing it at 1,000 milliseconds, aka 1 second divided by 12, i.e. 12 frames a second. We're updating this drawing. And here you'll notice instead of that square shape, we've got a smoother up and down oscillation because I created an oscillator node and it's using the default sine wave. But our peaks aren't touching the top and bottom of our canvas because our gain is cut in half. If I had full gain, we'd see those oscillations going all the way from the top and hitting the bottom. Now, this is kind of a useful little snippet of code. So what I've done is I've actually encapsulated it into a little function, which I'm using in this next demo. I'll talk about that change there that we saw, but I've created this little create canvas function to just create that canvas. It takes an object with a couple of parameters, the element that we want to put our canvas inside of, and the instance of our analyzer, whatever that variable happens to be. And then it'll create a canvas using that data and stick it in whatever element of our page that we want. I've actually, throughout these examples, created a bunch of little helper functions. Like I've talked about before, instead of using a library, we're using, since folks were talking about wanting to do more deep dives, I'm using just the API directly, which I think is cool because, like I said, the API does give us a lot of low-level access, like this audio buffer, but gives us a lot of high-level, easy sort of control, like these oscillators we're using. So we don't necessarily need a full library, but it'd be nice to not have to, create a whole bunch of other stuff from scratch. So I've got throughout these demos a bunch of little helper functions. So not really a library. It's almost like a deconstructed library that we can import piece by piece. And for those of you especially that dive a little deeper, if you see me using a little helper function that I've created, on all the examples, I've linked to what that helper function is down here. So if there's any dependency being used in this example, you're not just going to be able to copy paste this into your code. You're also going to need to make sure that you've got this function included in your project. So in our case, right, this wave canvas, you can just click on that. Here is all of the code. It's essentially that same code from the last example, except I've added some little error checking just to make sure that the right parameters get passed into the function, as well as some defaults. And I've also got some comments here that explain how to use that function, including what other parameters you can send, maybe to change the default color of that line and stuff like that, and also to change the default frame rate. So if you see a little helper function in any of the demos that I'm using and that you'd like to use, you can just copy that, create a new file, paste it in, and then I've tried to stick to this convention. Most of all of the these little helper functions I've put together have some info here, and then an example of what it looks like to use it. What are the required options that you got to send, but what are some optional options you can also send into it, so that then we can use it in our code. Now, keep in mind, just because you have a JavaScript file in your project doesn't mean your website knows about it. You've got to import it. So I'll import my wave canvas before my main.js so that my main.js can make use of the function inside of the wave canvas, which is just called create wave canvas. Now, like we notice in this example, the create wave canvas assumes a couple of things. It assumes that we've got some element on the page, which can be, maybe like an ID, or a class, or just the name of an element if it's the only element of its kind on the page. So I'll do that. I'll add a section element over here, and so this is the element that the canvas is going to be injected into once it's created. And the canvas also assumes that I've got an instance of an analyzer node I've called mine FFT. So I'm passing that in FFT. Now, if I refresh my page here, I see that canvas showed up, but I don't actually see the wave shape because this is what my project looks like currently. I've created an oscillator. It's my tone. I've connected it to my gain over here, and I've connected the gain to the speaker over here, and I've also created an analyzer over here, and it's just hanging out on the side. It's not really being used. So what I want to do is connect my gain also to the analyzer, right? Because it is no rule that says I can only connect a node to one other node. I can connect this oscillator to multiple gains or to other effects. I can connect this gain to multiple outputs. So by sending the data into here, then to the speakers means I can hear it, but then routing that same data over to the FFT means I can visualize it as well. So I'll need to do that. I'll need to also connect my level to my FFT. So that means that data is also going to get routed over to the FFT, which can then be drawn to the canvas. Cool. So the last sort of intro details I want to cover here before the next video where I'll talk about the actual assignment and some examples, some music theory, and we'll look at what it looks like to algorithmically compose stuff using these tools, this Web Audio API. Last thing I want to talk about is actually some parameter methods. So these parameters, all the parameters with numbers that source nodes and processor nodes have. Oops, put this over here. These parameters like gain and frequency, we can change them immediately by doing something like this, right? Level gain dot value should be 1, or tone frequency dot value should be 880. But in the same way that we use start and stop to schedule the start and stop according, at a particular time in our audio context's timeline, we actually have methods for scheduling changes in the values of different audio parameters, like frequency and gain and the parameters that exist in some of those other processing nodes. And those are set value at time, linear ramp to at time, and exponential ramp to at time. Exponential ramp to value at time. Woo, that's a mouthful. So what does this look like? So again, instead of just saying I want to change the volume to 1, I can say level.gain.set value at time 1, and then the time I would like to schedule that change at. Maybe ctx.current time plus 1. So what I can do, again, it doesn't matter what order I put any of this stuff in, because they're all going to run at the same time. They're going to create that schedule, right? They're going to mark the future timeline points where these changes need to happen. And then when the audio context gets there, it'll do the thing that I've told it to do. I'm just putting this here now visually so that the code looks like the order it's going to operate in. We're going to start at a current time, then a second later I'm going to set the value to 1, then 2 seconds later I'm going to stop the tone. Let's try that. Cool, so you saw that? We noticed that the volume was at, and actually let me start the volume even lower, at a quarter. There's quarter, max, gone, right? It was a quarter for the first second. Second later, we saw the volume kick to max, and then a second after that, we're flat because we stopped. But like I said, it doesn't matter the order that I write this. We get the same result because these are scheduling the changes for the future. We're talking seconds into the future, but these are scheduling functions, not triggers. It doesn't matter the order we write them in. It matters the time that we told these things to get triggered at. So set value at time does a quick jump, right? It's just a quick, jump to that value from whatever it was at to whatever we want it at. But we could also do a linear ramp. So let's say, a second later we go to 1, and then instead of stopping, instead of like that hard stop, right? Oh, it goes immediately to silence. What if I wanted to fade out? So I'll say, then I want you to go to something real small, like 0.1 at 2 seconds. So at the same time that I'm stop, I want it to be 0.1, but at a second before that, it's going to be 1. So between this second and this second, I'm going to linearly go from 1 to 0.1, meaning instead of a quick jump, it's going to go 1, 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, and it's going to do that over the course of a second, right? Between current time plus 1 and current time plus 2. You see that? This initial set value at time, that's a quick jump. So we go from a quarter to boom, to max, but then we fade out. So if we want to do smooth changes over time, we have linear, and we can also do it exponentially. Right? So the difference is like linear curve. Linear curve is essentially not a curve. It's just a straight, it's one of these. We go from 0 to 1 consistently. But an exponential curve, exponential, God, whatever, the internet will know what I mean. An exponential curve looks like this. We go from 0 to 1 initially slowly, and then we ramp up. So we've got set value at time, linear ramp to value at time, exponential ramp to value at time. And so we can combine these in interesting ways. This is the last thing I want to show you, but before that, let's just a couple little gotchas, a couple little unexpected behaviors which you might come across. So let's just talk about them now. So I did this a second ago, and then smooth fade. So what if I had done this? Then does that mean, am I going to go from 0.25 smoothly up to 1 and then smoothly back down to 0.1? Nope, I jumped. It's because the first linear ramp to, like, this initial value was set, initially with a creation. I didn't set it with one of these methods, and these are responding to other to values as they were set with these methods. So if I wanted a smooth ramp up, I probably have to also do this. I'd have to say that initially, when we start our tone at the current time, let's set the volume to exactly what it was at. I'm not really changing the volume, but I'm setting it using this method, which is now going to guarantee that I'm going to go from here to here linearly. Right, so now I got to fade in and then fade out. The other weird gotchas, notice I didn't put 0 here. That worked okay. But I've noticed when I've experimented with the Web Audio API in the past, and maybe this has been an issue across different browsers actually, now that I'm thinking about it, that 0 makes it act weird sometimes. So if you do want 0, I'd recommend something like 0.001, which is practically, for all intents and purposes, 0. Right? We went down to a thin line, but it'll avoid little bugs. So this is just a little couple gotchas. Make sure that you've set some value at something before you do a linear ramp, and if you want to go to 0, don't. Just get real close. So now we can create some nice, like in those initial examples, our oscillator just kind of like showed up, started playing, and stopped. It's a real harsh on and off. And that might be cool. You might create algorithmic compositions that have that aesthetic. You might want that kind of sharp on and off effect. But most instruments don't really sound like that. Like most instruments, the volume kind of cuts in and cuts out. Like if you pluck a guitar string, which is quite literally creates an oscillation, right? The string is oscillating up and down, which is moving the sound particles in the air, just like our speakers do when they oscillate back and forth. And thus we can hear those oscillations in the air with our human sensors that we call ears. That oscillation that guitar string makes doesn't go from 0 to 1 in an instance and then doesn't just go quiet. I mean, unless you have a guitar string, ringing and then you like put your hands on the guitar to silence it immediately. Usually it fades out, right? And there's a particular pattern that most instruments follow, which we call ADSR. Now ADSR stands for attack, decay, sustain, release. So, and these words, attack, decay, sustain, release, are describing durations of volume, of changes in volume. So the attack is the duration from the initial plucking of that string up until it hits its peak volume. The decay is this little subtle drop that happens, right? Because it kind of hits this peak volume and then it kind of settles kind of drops down to settle at a normal kind of sustained volume. So the sustain then is, so decay is the time it takes to go from that peak to that sustained value. And the sustain time is the time it kind of holds the note at. So it kind of holds that tone before the release happens. Release is sort of the opposite of the attack. It's when that sound goes from that sustained value and fades down to nothing. So this kind of volume pattern over time with this attack, decay, sustain, and release, we typically in sound engineering land, we call an ADSR envelope or something. Something like this is typically what it's referred to. And we can create that type of sound like this, or that type of envelope, type of ADSR effect, by saying like, all right, here, how long do I want my attack to last? How long do I want my decay to last? This kind of drop. How long is the sustain? And how long is that release? So in this little example, I've said the attack is going to be half a second. It takes from silent to the peak volume. Then the decay, it kind of drops down real quick at 1/10 of a second. Then the note is going to be held for a full second. It's the sustain, and then it'll take just as long as it took to come in. It'll fade out. The decay will also, the release will be half a second, and then I can create a combo: a set value at time followed by 1, 2, 3, 4 linear ramps. These are linear. I could also make these exponential changes if I wanted to. And then I'll create a variable for my current time. And then what I do is like, all right, the gain is going to start at near 0 initially, as soon as, my current time, as soon as my context is created. Then I'm going to ramp up to a peak volume. This peak volume here, the y-axis here is volume. The peak volume of nearly 0.755, before falling down for decaying down to 0.5, sustaining at 0.5, and then going back down to 0. So those are the changes in volume, and they're going to be scheduled at these times. Initially, I set it to the current time. At the current time, I set it to 0. Current time plus the attack time is when I want the attack to hit its peak. Current time plus attack time plus decay time is when I want the decay to happen over here, right? Here's current time, attack time, decay time. Then I want it to stay at 5.5 until the end of this sustain period. So again, current time plus attack plus decay plus sustain. So over here at this point this x-axis is time, at this point in the timeline. And then at this point in the timeline is when I want it to fade out from here to here. So I add the release time. That's when I want the fade out to happen. So this is the code used to reproduce what, like in music software, we might call like an ADSR envelope. I linked to some other notes there if you want to learn more about that. This functionality is another perfect sort of thing to encapsulate in a function, because then we could reuse it across multiple notes. And so now all of our notes can have that smooth fading in and out sound. So here what I've done is I've taken that same logic that I just showed you in the last example, but I've modularized it. I've created a function called ADSR, and rather than hard coding those values in here, I'm passing them in as parameters to this function. First, what's the param, the audio param that I want to change the value of, right? The param. So in this case, down here, I'm passing in the gain of the level of this level variable, which is an instance of the gain node. I'm passing in that gain as the parameter. I'm using that also to determine what the initial value of that parameter is. So that's the starting point. Then I'm also passing in a peak volume and the sustained value, peak and sustained value that I want to hit as the next two arguments. In this case, 8 is the peak volume and 7 is the sustained level. And then I'm also passing in the start time and the ADSR durations to reproduce that same logic. And so then what that lets me do is create something like this. Right? Because what I'm doing is I've set my frequency of my tone to 440 to an A, but then I trigger this ADSR volume. So instead of just a quick A note, it kind of smoothly comes in and out. Then I change my tone to a C. It's the frequency for C. Also with an ADSR, change it to E. Also with an ADSR, change it to back to C and back to A. Each time changing the volume of my level in this ADSR envelope sort of way. Okay, so those are the basics. This is our template. Probably going to be uploading something like this as the actual repo for the assignment. I'll probably remove some of this code, make this little, or maybe I'll leave this as an example. But in the next video, we're going to take these basic pieces, maybe also talk a little bit about audio buffer and a little bit about music theory to kind of set you up, to give you some examples for how you're going to use these otherwise pretty primitive, pretty simple kind of methods here, these little bits of the web audio API to generate some musical compositions. So this is where we're going to get into the algorithmic part in the next video.